have to hang up the phones here. We'll get started. 4 people will come in. Right? Yes. Can we get that on? Okay. You want to do that, is it?
We need to use these mics. Yeah, these mics, yeah. And these mics also record the things. Yes, yeah, the one which they are going to use, that's going to record. But with that, they will have to use. Oh, both have to be used. Yes, yes, yes. Because that mic is just going into that recording. This one is only going to the mic. Yeah, no, but I heard this on the recording as well. No, not the wrong one. No, not this. This records.
In other words, if you get about 20, 30 questions this first meter, you can't answer all of those, he will decide which one of the getting answers. Yeah. Right, over to Narayan, you go where this whoever the speaker is. Just review that one. I don't need the. This also goes on. So I'll give you public address. During the question minutes, just wait for the microphone. That way we get your audio on.
Hello? This one? Is it working?
Works?
Yeah.
One second, I'll just get the previous. The PA mics. Oh. Hello. Stop.
Hello? Bose speaker size. In Germany they call it Bose.
Bose. Yeah.
Normally
They
Bose.
had a dominant run, right, for 3 decades now.
Who?
Those are guys.
Oh yeah. I mean, of course there are competitors as well. Sennheiser and all these. Marshall and
They
everything.
haven't really clawed away at these guys at the top end. What explains their dominance? Because their patents can't possibly last 20 years. They expire.
Yeah. No problem.
That's fine.
Yeah, sure. No. Okay. So, first of all, welcome to all of you guys. Thanks for making it so far. I'm sure that a lot of you have slept only a few hours because we didn't have much time to sleep and wake up in the morning to get here. It's the same for all of us. I also slept only like a couple of hours. So, I hope that we will not bore you out and make you sleep out here. And instead, like try to instill some more motivation and enthusiasm, although the mission did not go fully as planned. So the idea of creating this event was that there is a lot of new space, what we call as new space. I don't know what you guys understand as new space, but essentially the community of what we call as new space is actually a community of space entrepreneurs and innovators who are trying to build their own products and services in India, out of Bangalore and other cities. And these are prominently young people trying to, like build up their career as independent folks who will build their own space technology products. So, there's only very hardly like 2 career choices if you want to do space in India at the moment, in India. Either you can join ISRO as a scientist and you can grow up the ranks, and probably will take you 25 or 30 years to grow up to a certain level where you can, reach some level of decision making. Or you can join the private sector that works with ISRO, which is prominently some small industries that are catering to ISRO's demands. But unfortunately, a lot of these industries, they don't have their own IP. They actually get all of their intellectual property from ISRO, and they are only manufacturing some of these things. So if you end up joining some of them, don't expect to design anything, but be involved in more of day-to-day kind of manufacturing activities. So what we are trying to create as a community for the first time in India is an independent community that will not only work with ISRO and other the industries that work with them, but actually for the first time in India build space products that will actually take India into the world map, as in exporting India's space capabilities as products and services outside of just the launching of satellites that ISRO does. So the event itself, we wanted to put this together so that we expose the landscape, we expose some of the entrepreneurs who are doing things here in Bangalore, and maybe it's an opportunity for also you guys to see if there is a fit between what these entrepreneurs and innovators are doing and also see if this matches your career goals or something, and you can talk to them and get internships or jobs or whatever you want to do with them, right? So that's the entire goal here. So we don't have any slides by any person here, so you don't need to look at the screen. In fact, you can switch off the screen as well. And because we didn't want to have people look at slides and just get bored at it. So the whole format is based on just 15 to 20 minutes of just talking, talking about their life story, about how they began, where they were, how they began, and everything, and where they stand today, and what are the challenges ahead for them. And then after 15 or 20 minutes, you are free to ask questions for about 5 to 10 minutes to the speaker. And then maybe if there's time at the end of the day, we'll have another round of question and answers or a session. So it's left to the speaker if he wants to take questions, during his speech or after the speech. It's all left to the speaker. And you are also feel free to interrupt if you have any questions or so on. So this is not like a formal, scientist, whatever, crowd talk or usual stuff. So just try to get as much as you can out of this event, and we hope to keep you all in the loop as we grow the whole community of NewSpace here in India. So firstly, I'd like to welcome my friend Gangadhar to come and speak. So just to give you a brief profile before he goes deep down, Gangadhar runs possibly India's only carbon nanotube reactor in Bangalore, and probably the world's best carbon nanotube reactor here, which is running here in Bangalore as well. So he is a good friend of mine, and he was studying in the US and actually finished studying there, and actually came back to India and set up his company about 7-8 years ago. And funnily, he'll talk to you about his company story and what his company's name is and everything else. I don't want to take away all of that from him. So so over to him.
Okay, thanks, NP. Yeah, sure. So morning, everyone. I'm Gangadhar. So I'll just walk you through like a brief history of what we have been doing, what carbon nanotubes have to do with space, and why am I even starting it with nanotubes and materials. So for me as a child, I've always been fascinated with space. It was like so enticing and so beautiful. And I wanted to get up and be there in space, travel regularly and do all of that stuff. But I also, fresh out of school and college, I looked at, okay, if I really wanted to get into space, what are my chances? And then I decided, okay, so back then, 10 years ago, India had not announced any kind of a space program to send humans. It looked like, okay, we are only happy sending satellites because our space program's mission is that we want to have beneficial effects of space. We don't care about anything else. And even if we want to do it, we wouldn't be touching it. That was the mandate. And also I realized that, okay, if I have to get into space on a government-based mission, the probability is very, very small. There is too many factors, and there are too many reservations and too many things that multiply, and ultimately at the end of the day, I wouldn't have control over getting into space. So it has to be a private sector endeavor. Now, private sector endeavor, if we as Indians, we want to do it elsewhere, we'll never be the first in that, because nobody else would want to have us being the first in their countries. They would want to have their people being the first. So I identified that could be a lacuna. So we had to be an Indian-based thing. It has to be a private endeavor. It has to be something that has to be able to get us there regularly in a safe manner. So all of these factors, just started putting them together. And then I started, okay, so it's clear, it has to be a private sector endeavor, because that's the only way to get there regularly. But a private sector endeavor, nobody's going to put money on it unless it's profitable. So we have to showcase how it's going to make money for someone, to make it profitable. Now for someone to make things profitable, you want to have a regular access and repeatable access. Now if you look at space, and if you look at the human-rated space missions, then our rockets of today, the safest rockets, you can have one failure out of 500 launches. That's NASA's acceptable for human-rated launches. During the Apollo launches, the safety factor was you can have 2 rockets blow up for every 100 launches. Now it seems ridiculous, just think of it. Like on a weekly basis, if you're traveling in any of these rockets, you're allowed to die 2 times. And that's ridiculous. Like, how are you going to have regular access and do anything in space if you're going to have to die every time you take it for a week? And so the only way to make things safer, and the reason why this happens again is because we have to push our materials to their limits. Existing materials that we have, our best steels, our best aluminums, they can only take in about a 20% or a 10% more stress than what we design it for at the material's theoretical limits. So because of this low factor of safety, and this again comes from the mass considerations that we have from getting out of Earth's gravity wells, so we have to make things extremely light. That means shaving off every material that we can find to make it light. And that means lower safety, and that's the compromise we have to take to be able to get up there. So the solution for that is we need something that's extremely strong and light in weight. So while I was studying in college and was taking up summer schools in astronomy at the MP Birla Institute of Fundamental Research, and also took up a honors diploma at St. Joseph's College, which was sponsored by IS Aero. So these folks said, okay, we need strong materials, that's what everyone is saying. And when we Googled for what are the strongest materials, it said carbon nanotubes. So that was the highlight for every magazine. Every astronomy magazine said this is the future. And people were also talking about some new concepts of getting to space, something called a space elevator, where they said, okay, why take a rocket where we can just build a lift from Earth to space, we'll just get on the lift and get up there. And that could be straightforward and simple, but the only way to make that is, again, you need something extremely strong. And the strength numbers said that you need something that's 100 times stronger than steel. So I was stuck with, okay, so if at all any of these private sector endeavors are going to happen, if at all people can regularly go to space, not just the robots, then we need to have something that's extremely safe and light in weight. And this meant carbon nanotubes. And when I looked at the state of art of carbon nanotubes while I was graduating from college, I found that it was a disaster. So nanotubes were first discovered in 1991. And the funny backstory behind this is that they were actually discovered in starlight. So one of the researchers called Kroto, he had been observing starlight, and he found that there was a particular spectra that did not make any sense. It seemed to come from interstellar dust. It seemed to have like this carbon-like signature, but it was not really any kind of carbon that we knew of. And he happened to meet another researcher called Richard Smalley. So Smalley was at Rice University, he was a professor, and he also happened to be the world's most powerful laser. And what Smalley did with this laser was that, like any little boy, he just took whatever he could find and you'd fire his laser beam at it and blow it up and see what happens with it. He was having fun with that. So Kroto came up, Smalley, they were having a chat like on a sofa like this, and Kroto said, okay, see, I can't make sense of this. Can you just blow up a few carbon particles and see if you get this spectra? And he said, yeah, I'm fine, like this is a new thing, let me blow it up. And they did that, and to their surprise, they found that they could recreate the spectral signature they were getting from the interstellar space. And they did more analysis around this, and they were able to create a new structure of carbon. It's called a fullerene. It looks like a football in shape, and it exhibits the exact same properties. And then as a next step in this, as people started looking into this, this was the first breakthrough because carbon was never thought to be able to form this kind of structures. We thought all forms of carbon are practically known. So then as a next step, people started growing longer tubes. And one researcher in Japan found that these tubes could have like this football-like structure, but you could just stretch them like really long. And then someone else thought, okay, this is interesting, well, let me just put 2 probes and measure the strength. And it was found to be 100 times stronger than steel is. And that was insane, that you had a new form of carbon that was incredibly strong, and it seemed to be incredibly light in weight, and just everyone were hooked onto it. Like, this is the future, and we have probably hit it right there. And people also found some more interesting properties. They found that it can withstand a lot of heat. It can withstand a massive amount of temperature without breakdown. It can also withstand a lot of current. Now, it can withstand about 10,000 times more current than copper can. And another very interesting aspect is that it's also radiation resistant. So here you had a material that had all of the properties that you could use for as an ideal space material, that it could be used for constructing new objects. Yeah. So you could use this. I'll just speak loud.
Okay.
Yeah.
Everybody can hear, right?
Yeah. Okay, so I'll try to balance with that. So anyway, so you had to have the strong materials, you had to have it light, and so here was a material that was perfect in all aspects for space. And people have tried making this material in large quantities. I'm not the first one. And each time people tried making it, what we found was that we had to have these nanotubes in particular sizes and in a particular manner. It so happens that you can have a wide range and wide varieties of nanotubes that could come out of it. But to be practically usable, you need to have them in a very small diameter ratio. You need to have them in a very small distribution. And what this meant was you had to have nanotubes with a size of about 8 angstroms. Now, to just wrap your heads around 8 angstroms, So 8 angstroms is about 2 lakh times smaller than a single hair strand. So just imagine that, something so tiny. Another way of looking at it is that the tubes that are made have to be so small that they can fit 1 molecule of water, just 1 molecule and nothing else. You can't place 2 of them. So that's how tiny these tubes need to be, with an error margin of 1 molecule. So now, so this was an insanely big target. Like if you have had a chance to look at any of the mechanical instruments that go around you, they have huge errors. Like if oftentimes, like for a table like this, it's a centimeters, a bunch of millimeters off. Most metals and bodies are millimeters off. Precision machining that we do right now is like in microns, but never in nanometers and molecules in sizes. So this was a manufacturing challenge. And before us, what people did was they used to grow the nanotubes. There used to be like substrates on which they used to place particles and grow them. So what we did was to come up with a new technique for growing them, along with help from Smalley. It uses a vapor process. So what we do is to take a gas called carbon monoxide. We pressurize this gas to a very high pressure. We go up to 100 atmospheres. That's equivalent to about a kilometer of water in pressure. Then we increase the temperature of these gases to 1000 degrees Celsius. That's like 3 times the temperature at which the human body will vaporize. And into this boiling cauldron of a system, we inject iron particles one by one. And these iron particles are broken apart into single atoms. And these atoms then come up into the nanotube form. And we maintain these conditions consistently. And when we're looking at the challenges of this, one way to wrap your heads around it is, like if you think of a rocket engine, it produces a lot of carburization from its hydrocarbons that are present inside it. So it's typically designed to operate for about 300 seconds, after which the whole system clogs up and there's nothing you can do about that. But the reactors we built have to operate at similar conditions with very similar systems, but they need to operate for weeks and months together without clogging up. So that was the major challenge that we had to address. It took a long time, and maybe if someone asks a question about it.
How do you heat the gases?
So we use resistive heating. So we take a long time to heat them step by step or a long distance, and that brings us up to the temperature. Yeah. And so also with gases, like there's this funny thing that you can't heat them up instantly. You have to apply only a small amount of heat slowly for it to get to the temperature, otherwise it doesn't work. And so, and also it's like just clever mixing of gases to get to the temperatures for the iron particles and stuff. And so later maybe someone asks a question, I can tell you more about how these systems are built and how we got through on that. Now, after we made the nanotubes, next we were always talking about space, because that was the main agenda for making the nanotubes in the first place. So what we did was we went to the government labs that have been building all of the technology for ISRO. So one of the labs called CMTI in Pina is the premier manufacturing technology institute. So if you can think of anything that's the most advanced manufacturing tech in the world, those instruments are present there. And these guys spend a bomb on everything. And so we went there, we convinced those folks to take images of the nanotubes we had made. It turned out we had made something that was 100 times smaller than the best nanotubes that they had made in their own facility. And so they put up a poster out there, it's even there today. So when you go to the electron microscopy lab in that particular facility, you see a big picture of nanotubes and NoPro's name there saying that this is where we got the nanotubes. So ISRO happened to go to them and tell them like, see, hey, we need like nanotubes to make this black structure, potentially for use on Mangalyaan. So, and those folks were like, okay, you just go to this company and they will help you out. Don't worry about nanotubes and stuff. So when ISRO came to us, the requirement that they wanted was, they wanted a black coating to go on star trackers for potential use on Mangalyaan. So what this material does in this particular application is, it absorbs light. It absorbs it so well that the star tracker enables the spacecraft to see very, very faint stars. So when it can see the faintest stars, it can get a better position fix. So it can burn much lesser propellant for its corrections and be on the pathway without having to get into too many deviations. So this was the application for them. So we were able to deliver a prototype for them in 24 hours, and that's unheard of for anywhere. And so we were able to take some of these astronomy lasers, create a thin coating of the stuff, and make a quick video of it and show them how a micron thick, like 100th of your hair strand, could block all light from an astronomy laser. And so ISRO saw that, and then immediately we started the project. We created like new polymers and developed it, and it got space qualified. So this was one work, but then ultimately what happens is, when you think of things from a business perspective, as a startup, you also want to show the revenues. You have to show how much it can grow into, what it can perform. Now when we looked at black coatings as a revenue source, it's actually very, very tiny, because the number of vehicles that require, the amount of surface area that exists for them is actually very small. It's not a major revenue generator. But luckily it so happened that the tech we had developed, the polymers we had used for working with ISRO, it also happened to be the same polymers that are used on aircrafts. And we got a contract with Lockheed to use this on all aircraft, but for a very different application. The same black coating is actually used as a lightning conductor. So it so happens that when you have composite bodies, they cannot conduct lightning, so you have to apply a layer of metal on top of them. So even with rockets or windmills or anything, when you are parking them and when you have a bad weather condition, you don't want them to be there unless they have a lightning protection on them. So right now the only way to do it is to make a metal mesh. The metal mesh adds so much mass that it makes it pointless to just go over the composites. But now with the nanotube coatings, you can reduce that completely. So that's one major application. So as a next step, what we have been doing is to use the nanotubes in more use cases. So recently, if you've been seeing the news, there have been a lot of applications coming out of nanotubes, and most of the researchers are someone that we are in connect with because of the tubes we make here. And so on the material we make from here, there are about 15,000 research articles. So every aspect of it is understood when it comes to applications. So some more of the space applications are colleagues at NASA, what they've been doing is to use these inside composites, and particularly the plastic bodies for micrometeorite protection in spacecraft. So what happens is when you have a micrometeorite hit a spacecraft and makes a hole through that, you want to have some way of fixing it and repairing that. So it turns out that when you have nanotubes inside these polymer structures, you can use a microwave gun and you can just pass it over the broken structure and it melts the whole region of the depth. Now normally when you use a microwave gun or anything, a heating element, you only heat the surface of it, not the true depth of it for getting the materials to join together. So while the nanotubes allow for heat absorption through the depth of the crack, so you can seal it completely without any leaks. So this is one use case. Another friend from Boeing, she used the nanotubes to make tethers, long tethers, that were sewn onto spacesuits for potential use on Mars and again when we go back to the moon. Now what this stuff does is the nanotubes, because of their high conductive property, they act as very good repellers of the dust particles. So the use case there is like it's sewn onto the spacesuit. When the astronauts are walking there, they just press one button and all the dust ripples out. It just self-cleans itself. And they couldn't think of any other material they could use for the high conductivity that could pass through that. And this happened like the last year, and she got a PhD around this topic itself. And more down to earth, there have been a lot more applications, like some of the other use cases for the nanotubes, besides them being useful in space, have been in the biotech and biological sectors. Like some of the end users, we found that they could use it for mapping DNA molecules, which is like completely weird because, what they do is to attach these nanotubes to DNA molecules to make them glow up, so you can actually have a very bright structure coming up there. So you can analyze DNA, you can see the structure, and you can see how it's being modified and played around with. And we also had one experiment where we fed the nanotubes to silkworms. So this was a favorite. We were just curious to see what happens to that. And we ended up finding that silk becomes 5 times stronger. So it could potentially make for very strong and high modulus clothing and stuff. And so these are some use cases. But very soon in the next couple of years, what I see is the nanotubes starting to make their way into structural materials that have our structures become much stronger and lighter. And that as a crescendo effect is going to help us build much stronger, lighter structures and build safer spacecraft. So that's the direction we are in. And all of that work is happening right here from Bangalore. That's the proud part. So happy to take any questions, and if you have any thoughts or any comments, happy to answer, help you out.
Can we do a small recap for those who came late? Maybe just a couple of lines. Like just to know who he is, otherwise you don't understand.
Okay. So hi, for the newcomers, I'm Gangadhar. I'm from NoPro NanoTechnologies. So I specialize in carbon nanotubes for use in space. So we make this advanced material that's extremely light, extremely strong, and ideal and suitable for space for the future. So as we build massive structures and as we go up to space more regularly, this is the material that's going to solve that. And we're making that right here in Bangalore. So, and the agenda and context here is that if you're free to come up or ask any questions. If you want to know anything more, I'd be happy to share that and share insights with you. So I wouldn't call it superconductivity per se, but it so happens that inside the nanotubes, there is no resistance for electron flow. So the electric fields present inside them, the electrons are just floating inside. And they just pass through in something called a ballistic mode. That's 1,000 times better than on any surface that we can use them on.
So can we weight the conductivity?
Yes, we can. So depending on the diameters of the tubes, so we call it the twisting of the tubes. Depending on the twist, we can actually make them semiconducting or metallic completely. So on the manufacturing, we can control that.
And I have a more late question. So if these applications really have to become, say, more affordable, what are the applications besides in space and in aviation and in automotive would you contemplate?
Okay, so we were actually making a list of that just to see where nanotubes can get into. In our list, we found 120 different applications. So I often call the nanotubes as a Rajnikant of materials. It can do anything and anywhere. And so in an interesting way, so they have use cases in biotech, particularly for the DNA fluorescence. And they also have a use case in water filters. So it so happens that this tiny size, when you make them at 8 angstroms, the nanotubes act as conductors of water molecules. So when you place a water molecule inside them, it moves without resistance. So instead of having a filter, normally a filter is about creating a mesh, but here there's no mesh. It's just taking in water and moving it through that. So I don't know what to call it as a different thing. But it could be used as a potential filtration device for desalination and other potential effects. And there are other use cases too, like so there's been a kind of nanotubes called the Vanta Blacks that's been used as black coatings. It's been used in paints and stuff to get an extremely black surface. So there are a lot of use cases around that. Like you can name any field and I can tell you how it can be used.
Questions? Yeah. So what we're going to do is you're going to start passing the mic around. We have 2 mics. So we'll hand one mic to this side and one to this side. The moment you're done with your question,
Okay.
whoever is going to ask the next question will take the mic. Put your hand up so that you can.
Yeah, first.
No. Don't mess with the button. That's just a recording mic.
Okay. First of all, good morning.
You'll have to shout now. You're the house captain.
Okay. Oh, first of all, good morning. Actually, you were talking about the meteoroid regarding its application in micrometeoroid protection in space. So, does it work similar to a Whipple shield, or else what actually like you were talking about? Can you please explain me a bit more about it?
Sure. So there are a couple of different ways of using it. The one I talked about was on the composite and plastic, the thermoplastic components that go on the spacecraft on the top layers. So when you have the micrometeorites strike through that, and when you need to fix those holes, so that's when the nanotubes make a big difference, because you can use a microwave gun to fix those ruptures. And what happens is when you have that through hole happen, or when that hit is there, and you create a crack, if you were to use heat to repair them, the heating will only affect the top region. It won't affect the complete hole. Now when you have microwaves and when you have nanotubes are very good microwave absorbers. Besides optical light, they can absorb a lot of wavelengths. So they absorb microwaves through the depth of the crack. So you have uniform heating throughout, and that helps seal the broken hole. So that way you have a fix that's through the hole instead of just the surface clean.
Okay.
That's the mentioned.
So, I have a question regarding the connection between the size of the nanotubes and the properties and the applications that you're talking about, the different applications that happen. Do you apply sort of different size tubes to each one of them, or is this a unified solution for all of these applications?
Okay, so with it starts becoming more fine-tuned, so we can actually make them, what we call with the nanotubes is chiralities. So it's about, so when the one way of imagining this is you can think of nanotubes as made from a chicken mesh wire, the hexagonal shaped wire. Now you can fold that wire in many different ways. Depending on how you fold them, you get different properties. Now when nanotubes are normally made,